Assalamualaikum warahmatullah. This is Pripili 462. Today's experiment is on RTL Synthesis, a gate level implementation of a full letter using Cadence Genus. So we have already learned what RTL Synthesis is, what is its position in the ASIC design flow, what are your .p files, .sdc files, your TCL scripts and all of that. And we have already seen that we're using a full adder as an example in order to do the RTL synthesis. And we have created our desired directory for the RTL synthesis environment. Then we have written down the codes. And then we have done it manually at first. And then we also did it automatically using a TCL script. And finally, what we saw is we launched a graphical user interface in order to see the schematic view. So we have done all of that, and what remains is discussing about the outputs. So if you recall, our output structure looks something like this. So in our output, we have a netlist, which is our main output. And we have various reports of our area, gate, timing, power, the summary of our design. So we are gonna see all of this one by one. So let's start with our netlist. So this is our netlist that our RTL synthesis produces. And our netlist is something that is unlike our RTL code, unlike our RTL design, which basically describes the behavior of a full adder. But this netlist basically describes the circuit as an interconnection of actual standard cells from the target technology library. So the first two lines, the input and output declaration, are self-explanatory. So I'm gonna start from here. Why is it wire A, comma B, comma C in and wire some, comma out? So basically, these are three input signals of the circuit. They're declared as wire because they are a synthesized netlist, and signals represent physical connections here between the ports and cells rather than variables. So earlier, A, B, C, I, C, O, S, all of those were treated as variables or register type data mostly, but in this case, they are wires because they actually signify physical connections between the ports and cells rather than being variables. So our output module consists of a single standard cell, our add fx11 or add fx1, and the wire declarations represent the physical connections that carry the signals between the module ports and the standard cell. So our C in A, B, C in, they are basically wire type variables. I shouldn't say variables, they are basically wire type data, and they are the input signals of the circuit. They are the input signals of the, let's say, circuit, and they basically denote the physical connection between your module ports or ports and cells. Okay, so just like our outputs, sum and C out, sum comma C out, they are the output signals of the circuit. They are the output signals of the circuit. And just like the inputs, they are also declared as wire because they are driven by the output pins of a standard cell. driven by the output pins of standard cell. So here you can see this notation A, first bracket A, B, first bracket B, CI, first bracket C in, CO, first bracket C out, and S, first bracket sum. This notation basically describes this physical interconnections. So if I just draw it, I think it will be a bit more clear. So let's draw. mm, So this is our standard cell. So this is our standard cell. It is at fx1 and it has some input ports like A, B, C, I, and it has some output ports S and C, O. Now the input signals of our circuit are lowercase a, b, c in, and the output signals of our circuit are sum and c out. So here they are connected like this, and they're connected like this. So hence the name, the physical connection between the ports and the cells. Here there is a single cell, our AddFX1 cell, and driven by the output pin of the standard cell. So the sum and output are driven by the output pins of a standard cell at fx1. So this is basically what is meant by wire type, as well as what is meant by this dot A, dot B, and your sum notation. So this notation basically means the interconnection between the input and the cell, and the output and the cell outputs. So I hope your netlist is clear. So if we read what is written here, the AddFX11 instant presence and optimized full adder hard cells selected by the synthesis tool during technology mapping. Okay. So the input pins A, B, C, I of them are connected to the input pins as I have already shown, and the output pins are connected with the output signals. Okay, and using a dedicated add fx1 cell provides a more area efficient, faster, and lower power implementation than constructing the full adder from separate XOR and an OR gate. So instead of XOR and an OR gate, if we just use a simple standard cell, obviously it would require less area, less power will be consumed, and routing will be smaller, so it will be faster, lesser delay, and all of that. So this is basically the netlist that is generated after our RTL synthesis. What was before a behavioral code has turned into a physical interconnection of the standard cells and the logic gates and all of that. So I guess we can move on to our reports. So the first topic was our net list. So now we can talk about the reports. So let's start with our area report and a lysis. So I have the report here, report area. So this was the area report generated by our genus. So all of these are not really necessary to understand. What is necessary is this part, and this part is the part that is mentioned here in this slide. The full adder is an instance. It has no modules and one cell count. Cell area is 5.13. Net area is 0. Total area. So there are a few things like the cell count, your area report as at first the cell count. It is self-explanatory because there is just one standard cell, right? The AddFX one. And it consists or it comprises of a cell area, which is 5.13 units. And there is another term called net area, which is 0. Now, what is this net area? Net area is basically the estimation of the wiring between the standard cells. So net area is basically the, this is a different color, estimation of the wiring between the standard cells. So if we had multiple standard cells, multiple logic gates, multiplexers or flip-flops and whatnot, then there would have been some wiring, right? The wiring is obviously done at the physical design stage, but the RTL synthesis actually estimates a connection between the standard cells and it translates that estimation into your net area. But since we have just one standard cell, so there is no interconnection between standard cells since there is just one standard cell, right? There cannot be any interconnection. That's why our net area is 0. So our total area is equal to cell area plus net area, so 5.13. This is basically 0. So our cell count is 1, cell area is 5.13, net area is 0, and our total area is equal to our cell area. So the key insight is one cell with 1.5.13 area unit confirms high efficient macro cell inference by genus. Obviously, this will be efficient because the macro cell, it consists of the uh, internal, what should I say, XOR and OR gate. It's basically performs the function of XOR, two XORs, two and two OR gates, I think. So obviously it will be more efficient than using single modules for each of the logic gates. So area report done. Now we have timing report. Okay, we have timing report. So timing report basically means, how much time it took to, evaluate the output from the provided input. So our critical path is basically from our input to our output, from our input through our standard cell to our output. This is our critical path. And this critical path is the data path delay. So the delay in this critical path is our data path delay. Or data path delay, which is our delay in the critical path, which is basically our actual propagation through our standard cell. It is 280 picoseconds. Now, if you remember correctly, in our SDC file or our synopsis design constraint file, we give our requirement to be 10 nanoseconds. Our required time or our requirement was 10 nanosecond. Was 10 nanosecond. That means any path from any input to the output should not have taken more than 10 nanoseconds. So 10 nanosecond is basically 10,000 picoseconds. This is the maximum allowed delay that we can allow. So what is our slack? What is our slack? Slack is basically the difference. Slack equal to 10,000 minus 280, which equals to 9,720 picoseconds. So we have a huge slack. We actually did not require such a big, time requirement. So since we use, or since the genus use a macro cell, so our delay in the data path actually reduced drastically, which made such a big positive slack. So our slack sign is positive depending on the sign of our slack. We will determine whether our design has met the requirement or not. So if the slack is positive, then our timing has met. Timing met. So the circuit is faster than what we require. And otherwise, our timing has been violated. And in this case, we had a positive slack. We had a positive slack. So our design constraint was met. But if we had if we had used a constraint of, let's say, 100 picosecond, then obviously our timing requirement would not have met and our design would have failed. But such was not the case. We gave a healthy delay time of 10 nanosecond or 10,000 picosecond. Hence, we got a pretty positive slack. So this was the second report. Then we have our power report analysis. So power report. This was our timing report. So the delay is this 280, 280, and our stack was 9,720. All of this was shown in your timing report. Now we're gonna see our power report. So this is our power report. So the only thing that we need to observe is these two lines, which is our leakage, our internal power dissipation, and our switching. And this is our total, and this is how much it comprises. Our leakage comprises of 0.12%, our internal 66.67%, and our switching is 33.21%. So let's see how we got all of this, or more importantly, why we got all of that. So our main power leakage is, or I should say our main power should have been leakage. This should have been the main power consumption. But the thing is, we are only using a single standard cell. So, a large chip with millions of idle transistors, leakage becomes the dominant power concern. So, leakage is basically the power consumption in idle state. So, for a single standard cell, the power loss during its idle state is very minimum, very less. But for, let's say, a normal design which has millions of transistors will have millions of idle leakages, and that would actually contribute to a very, very high leakage. But such is not our case. We have just one standard cell, hence we have a very small leakage of 0.12%. So what is our main leakage, or I should say what is our main power consumption? It is our internal power consumption and our switching power consumption, our internal power and switching power. So let's start with our internal power. So internal power is the power consumed inside the standard cell. Standard cell. So it happens why? For, let's say, two reasons. First one is short circuit power. So when the PMOS and NMOS conduct simultaneously, a short circuit is created, and this happens during the switching. So short circuit power consumption occurs during switching. So our internal power is consumed at the time of switching from high to low or low to high. And there is also internal node charging and discharging. So our standard cell consists of multiple transistors within it. Standard cell contains multiple transistors within it. So there are nodes in between these transistors. So whenever these transistors are charged and discharged, power is required. So this internal node charging, discharging, and the short circuit power during switching are responsible for our internal power. And this is the dominant power. And the full adder is purely combinational. Okay, every input change causes gate switching. Okay, inside the add fx1 cell, so it burns the internal power. There are no fan outs, hence the switching power is less. So let's come to our switching power. So our switching power is the power consumed outside the standard cell due to the charging and discharging of the external loads attached to the standard cell. So it is the power which is consumed outside the standard cell, and it happens for reasons such as interconnect interconnect capacitances. Okay, then there is fan out, and then there is, the output port capacitance as well. The parasitic capacitance, and all of that. So these are the reasons for which the switching power occurs. And it occurs outside the standard cell, unlike our internal power. So interconnect capacitances. So it is interconnect, as the name suggests, it's a connection between multiple standard cells, and we don't have any such interconnects. So there is no power consumption for that. Then we have the fan out. What is actually fan out? Fan out is basically the number of inputs driven by the output. So if we give just a normal example, let's say this is an OR gate. It has a certain output. Let's say this output is connected to three more gates. This is AND gate 1, AND gate 2. This is AND gate 3. So we have three AND gates which are driven by the output of the OR gate. So the inputs of the AND gates are driven by the output of the OR gate. So here the fan out is 3. So the more the number of fan out, the more will be the switching power due to fan out. As simple as that. But since we do not have any other standard cell connected to our add fx1, we do not have any fan out. But the output port of our standard cell itself has some capacitance. It has some parasitic capacitance, hence we are getting some switching power. But it's not enough to overcome the internal power. Hence, our internal power is about 66.67%. Our switching power is 33.21%. And finally, we have our leakage, which is negligible due to the presence of just one standard cell. So this was our power report. I think we have one more report left. Our gate count, it is pretty straightforward. So this is our power report, and we have our gate count report. So this is main thing that we're gonna notice, and we have it here in our slide, which is the number of instances. So our add is a gate count report. We have a single standard cell add fx1, and the instances is 1 as well. Maybe it could have been if we had a 4-bit adder, we needed this same thing, 4 times, right? 4 times. But we're just using a single bit adder, so we are not seeing multiple add fx1. We have just one instance instead of 4 for a 1-bit full adder. And the area is 5.13. We have already discussed about that. And now the type of cells, the type of cells present. Number one, we have logic. So we have one logic cell, which is our add fx1, our standard cell, and it comprises of 5.13 as usual. And there is another type of cell called physical cells. Physical cells. It is actually 0. It is 0 because There is no filler, tapper, or end cap cells which are inserted during the place and route. So physical cells are like filler cells, the cells which are used to fill the empty gaps within your circuit. Then we have our cap cells which are used for connecting to the plus 5 volt and ground. And we have our N cap cells. These are the cells that are added at the end of a row of standard cell. Our entire design will consist of standard cells, which are arranged in rows. So the physical cells added at the end of such rows is the end cap cells. So they are mainly inserted or they are actually inserted during the physical design, during the physical design, during placement and routing. So we have no physical cell. So we just have one logic cell, which is the add effects cell. So it is a single cell, highly efficient, no physical cells. And compare without add effects one macro gate count would have been 2 into 3 into 1, 2 XOR gates, 3 AND gates, and 1 OR gate. So 6 cells, so larger area, larger path. So everything would have increase in area, increase in delay, and increase in power consumption as well. So the gate count has drastically reduced due to the implementation of a macro cell. Okay, so that was all about the reports. We had one extra report, which is our design summary, which is basically the summary of all the other reports. So we don't need to actually see that. And these are some common errors and debugging. So one of the error that I have mentioned multiple times while doing the genus synthesis is, the directory. Many a times we're in the wrong directory, and from the wrong directory we try to run a command, we try to run a file, and it does not occur. So we always have to use the correct directory. We have to go to the, let's say, synthesis for running the genus. We have to go to the constraint for running the SDL and all of that. And library not found. Okay, we have to find the library path first. Then we have to read the library, obviously. Then Verilog syntax error. There could be error in your Verilog code. Module not found, elaborate, module is not found. Okay, module name in elaborate must match the Verilog module name exactly. So this is basically the command elaborate full adder. Full adder matches the name that we write within our RTL code. The module full adder. So both of these names must match. Otherwise, the design won't be elaborated. So, okay, done. SDC path error. Verify path from okay. I already mentioned this. Library load warnings. Okay, there might be some warnings as you saw while loading the library, so you can skip those. No need to be bothered by the warnings. So these are some basic practices for RTL synthesis. You can read it at your free time. And this is the summary: writing the RTL code, setting the constraints, loading the tools, reading and elaborating, then synthesizing, analyzing the report, and exporting the netlist. And finally, what we obtained is a one add fx one cell. Area is 5.13, delay is 280, slack is 9720 positive, and the total power, I forgot to mention the total power, which is the summation of our leakage, our internal power, and our switching power. So all of that comprises our total power consumption, and it amounts to 165.86 nanowatt. Our leakage was the least, followed by our internal, and finally our followed by the switching, and finally the most dominant one, which is our internal power. And all of those constitutes 165.86 nanowatts. So these are some questions that may come in the left final. So you guys may study this and take preparation for the left final while studying these questions. So this was all for your RTL synthesis. I have tried to explain all the topics from scratch as if you are a noob. I was a noob as well, and I tried to explain it in such a manner that anyone who is just getting started with Cadence will be able to understand it. So that was all. Thank you for listening. Jazakallah khair. Assalamu alaikum wa rahmatullah.